Hey guys, I'm Harjis and today I'll talk about what problem did transformers actually solve. So you've probably used ChatGPT or Claude today. Maybe you asked it to write an email, explain something complex, debug a code piece. It just worked. But have you ever stopped and thought, why does it work? Like, why is this thing so good at understanding and generating human language? There's one invention sitting at the center of all of it. It's called the transformer. And today I want to take you on the journey of why it had to be invented by showing you every approach that failed before it. So, what does a language model actually do? Before we talk about architectures, let's be crystal clear about the problem we are trying to solve here. A language model simply takes in a sequence of words or tokens and tries to predict what comes next. That's it. That's the core task. The cat sat on the mat dash. We are trying to predict the word mat here. Simple, right? But hidden inside this simple task is something deeply complex. Language has, well, long range dependencies. Words that are 50 tokens apart that are connected. Then it has ambiguity. Bank means something different depending on what surrounds it. So a money bank and a river bank can mean different. Then order. So dog bites man versus man bites dog. Both of them mean differently. And finally, context. The entire meaning of a word can shift based on what came before it. Every model we are going to discuss is just a different attempt to crack this problem. Let's begin in a chronological order. This year is roughly 1990s. Researchers want to predict the next word in a sentence. Their idea is pretty simple, that is, count. Yes, just count how often words appear together in large texts. An n-gram model says to predict the next word, just look at the previous n words. So a bigram, I want dash. It looks at how often different words follow want in your training data. Simply a trigram, I want to dash, looks at three word combinations and you can expand it. This actually works surprisingly well for tasks like speech recognition, spell correction, and even early autocomplete. But here's the problem. Imagine I say the trophy didn't fit in the suitcase because it was too dash. Over here, what's it? The trophy or the suitcase? To answer this, you need to understand the full sentence structure. An n-gram model here has no shot. It's only looking at the last two to three words. Also, as n-gram grows, right, you need exponentially more training data for every combination. Example, the quick brown fox jumps. Here, a 5 gram. So, the number of possible 5 grams in a vocabulary of 50,000 words is astronomical. So, here's where n-grams hit a wall. They are statistically powerful but linguistically dumb. They memorize patterns without understanding meaning. So, the missing piece here is that we don't have representation of meaning and we don't have long range context. So that's why we move to feed forward neural networks. This is where word embeddings are born. The idea that each word can be mapped to a vector of numbers and similar word cluster together in the space. Example, king and queen are close, dog and cat are also close, but king and dog are far apart. So they fed these embeddings into a feed forward neural network to predict the next word. Now, this was a simple leap. The model could now generalize. If it had never seen a fluffy cat but it had seen a fluffy dog, it could make reasonable predictions. The embedding space does the heavy lifting for us. But the architecture had a hard limit. A feed forward network takes a fixed input size. You have to decide upfront. You look at the last 5 words, 10 words, 15 words. You cannot look at the entire sentence dynamically. But there's no notion of sequences. We just flatten your context window into a vector here. Language is not fixed size, right? A sentence can be 5 words or 500 words. A story can span 2 paragraphs. So you need a model that can handle variable length sequences and order. That's what brings us to the next architecture called recurrent neural networks or RNN or RNN. The idea is beautiful in theory. Process language word by word, simple, and pass a hidden state from each step to the next. It's like short term memory. At each step, the network updates its internal state based on the current word and everything it has seen so far. Think of it like reading a book and taking notes. After every word, you update your notes. The notes represent your running understanding of the text. This solved the variable length problem for us. You can now process sequences of any length and it respects order. So, dog bites man and man bites dog produce different hidden states. RNNs powered tasks like early machine translation, sentiment analysis, and even speech recognition. But here's where they break. Try to remember what happened at the beginning of a very long sentence. By the time you reach the end, the hidden state is being overwritten at every internal step. Early information here gets washed out. This is the famous vanishing grading problem. When you train the network using backpropagation through time, the signal of this early word was important gets somewhere mathematically squeezed to near zero by the time it propagates back. The model literally forgets this. There's also a major problem. So RNNs cannot work in parallel, which means step 5 works on the output of step 4. Step 4 depends on the output of step 3 and so on. So you have to process words serially, sequentially. So on long documents, this is a painful problem as it takes a lot of time to train. Moving on, to solve this problem, we have the model of LSTM, also known as long short-term memory. The core insight is let's give the network explicit mechanisms to decide what to remember and what to forget. Simple, right? So an LSTM this time has three gates. Forget gate. So should I erase some of what I have remembered is what forget gate does. Then input gate, it looks at is this new word worth remembering or not? And finally output gate, what should I output right now? This cell state is like a conveyor belt running through the sequence. Information can flow through it relatively unchanged for many steps. So the model can in principle remember something from 50 tokens ago. Now, LSTMs genuinely worked better than RNNs. They powered Google Translate for years. They handled longer dependencies than plain RNNs. They were significant improvement, but they still had problems. The parallel processing issue didn't go away. We were still processing it step by step, and training a model was still taking a lot of time. And the long range dependency problem was also not truly solved, it was just extended. On really long sequences, LSTMs still struggled. Think of it like the conveyor belt has its own limits. Also, LH teams are complex, lots of hyperparameters, and they are pretty tricky to train. Now, that is what made us discover the encoder decoder architecture. So, the idea here is pretty simple. We use one LSTM to encode the input sentence into a single fixed size vector, a meaning bottleneck over here. Then use a second LSTM to decode that vector into the output sentence in another language. For example, the cat sat on the mat in English is simply compressed vector into right, and then it is passed to a decoder which simply produces it in the French language. This was powerful for translation, but there was again a huge problem. You are compressing an entire sentence or paragraph into one single vector. That's a huge bottleneck over here. The longer the input, the more information you are cramming into a fixed size space. Something has to give in, right? So researchers noticed that translation quality dropped sharply on longer sentences. The decoder was expected to reconstruct everything from a single vector. The fix had to be let the decoder look back at the encoder's full output not just a compressed summary. And well, that idea has a simple name called attention mechanism. The idea here is pretty simple. Instead of giving the decoder one compressed vector, give it access to all the encoder's hidden states. And at each step of decoding, let the model learn which encoder positions to pay attention to. Right? Imagine you are translating a sentence from French to English. When you are about to write the word cat, you naturally look back at the French word chat. When you are writing sat, you look back at the French word. You don't try to remember the entire sentence at once. You look at the relevant parts as needed. Attention does exactly this. It computes a score between the current decoder state and every encoder state, creates a weighted sum, and the decoder uses that weighted context to generate the next word. This was, well, transformative. The translation quality improved dramatically, especially on long sentences. But, well, attention was still being bottled onto an LS team. The underlying architecture was still sequential. You still need to pass words one at a time before you could even do the attention step. The question became, what if attention was the whole architecture? And that brings us to the final transformer architecture, which revolutionized the NLP domain, right? So, uh, in 2017, a paper named Attention is All You Need is released, and the title says exactly what it did. They threw out the recurrence entirely. No LS teams, no step by step processing. It's just pure attention. Let me walk you through what the transformer actually does. One, tokenization plus embeddings. First, the input text is split into tokens and converted into vectors, same as before. Next, we had positional encoding. Since there's no recurrence this time, the model has no inherent sense of order. So, we add a positional signal to each embedding, and this positional signal is just a mathematical fingerprint of where in the sequence each token sits. Then we have self attention. Here's the key innovation. Every token attends to every other token, and this is happening in parallel. For each token, the model computes three vectors: query, key, and vector. Query focuses on what am I looking for, key focuses on what do I offer, while value focuses on the actual content, what do I actually contain. Then for each token, you compute dot products of its query with all the keys. Take a softmax to get the weights and then do a weighted sum of all values. This means it in the trophy didn't fit because it was too big example can directly look at trophy and suitcase and figure out which one it refers to, not through a chain of LSTM steps, but this time directly in one single forward pass. Then we have multi-head attention. See, we simply run this attention mechanism multiple times in parallel. Each head learns to attend to different relationships. One head might track syntax, other one might look at co-reference, another can look at semantic similarity. Then you have feed forward layers. After attention, each token passes through a small feed forward network independently. This is where a lot of knowledge gets stored. And then you have layer stacking. This entire block, right? Attention plus feed forward network block. It's stacked many times. Each layer refines the representations. For example, GPT-3 has around 96 layers stacked. But well, what problems did this transformer solve, right? Back to our question one. Well, it solved a lot of problems like long range dependencies. Now, every token can attend to every other token directly. Parallelization, no sequential dependency. The whole sequence is processed at once. Then, scalability. You can keep adding layers, heads, and parameters to this. And finally, flexible context. The architecture remains the same whether your input is 10 tokens or 10,000 tokens. This is why we went from decent translation models to the latest GPT, BERT, Gemini models in about 6 years. But well, that's not the end of it. right? What comes after it is the main part. The original transformer was an encoder decoder designed for plain translation. Then it spawned two dominant families. One was encoder only models, and another one was of decoder only models. In encoder only models, example 20, example BERT, we use only the encoder part. It is trained to understand language. So pre-trained to fill in masked words. It is great for classification, search, and understanding tasks. While decoder-only models use only the decoder part, they are trained to predict the next token. This is what powers LLMs like ChatGPT, Claude, Gemini to generate the next word repeatedly and give you long outputs. The recipe is pretty simple. Take a transformer, scale it massively, more layers, more parameters, more data is what we mean by scaling. And you get emergent capabilities. New capabilities like reasoning, coding, summarization, even rudimentary world knowledge that nobody had explicitly programmed or taught the model. And that's the wild thing. We didn't design these models to reason, we just asked them to predict text. Reasoning, it turns out, is what you have to do to predict text really well. So, next time you type a prompt and get a coherent, thoughtful response, reasons, you are seeing the end of a 30-year journey. Ngram learned to count, ANNs learned to represent, RNNs learned to sequence, while LSTMs learned to remember. Attention learned to focus, and finally, transformers learned to do it all in once, in parallel and at scale. Even failure taught us what was missing. Every architecture was a step up. So, if you found this useful, do subscribe and stay tuned for more such AI insightful videos.